we're going to need reflexivity, symmetry, transitivity, as well as just whenever we apply the functions, we have to be able to replace the variables that occur in the functions. So we just need these additional 3 axioms. Okay, so let ring denote the collections of these axioms. We're going to analyze the word problem for k equals ring. But we need to define a polynomial ring first. And because most of our computations, most of our theorems, we need to deal with polynomials. So for ring R, we define R x1 up to xn as a set of polynomials over n variables and coefficients in the ring R. And the x1 up to xn are the variables. Formally, a polynomial is a mapping P that takes sequences of natural numbers to R, and it's going to be size n sequences, such that I in n to the n, pi does not equal 0. So essentially this is finite. So essentially we just cannot have infinitely long polynomials. We have to have only finitely many terms. So an example of how do we represent a polynomial using a function of this sort is consider pijk, so when n equals 3. And say this equals R1 if I equals 1, j equals 4, k equals 5. R2 if I equals 2, j equals 3, and k equals 6, and 0 else. And R1, R2 are just terms in the ring. Then this represents the polynomial R1 x1 times x2 to the 4th times x3 to the 5th plus R2 times x1 squared times x2 to the cube and x3 to the 6th. So essentially, the elements in the sequence, the ith position corresponds to the power that of the variable, and the function value gives us the ring value that goes in front. That's the coefficient of that particular term. So just a few notes and notations. 0 is the constant 0 function. So you give me any value, it's going to spit out 0. And this will be useful because one of the big results relies on having a polynomial reduction to a 0 constant. And we're going to talk about that later. It's the big result. The big thing about what we're going to do today is polynomial reductions and answering some special question to determine to decide all universal formulas in the language in the theory of rings, and also in particular ring theories. But that's later on. We'll talk about that. So 1 is the function mapping 0, up the it maps the 0 function, not 0 function, the 0 n tuple to 1, and everything else it maps to 0. Minus p is just, well, what it usually is evaluating minus p to the m for every m. P plus q is just pointwise addition, and p times q is the following multiplication, which is typical, where each, so we're going to sum up p of m1 times q of m1, where m1, m2 multiplied to equal m. And where standard monomial multiplication is defined by I1 up to In times J1 up to Jn equals I1 plus J1 ... In time plus Jn, of course. So for also the big idea is also that we're working in a logic system. So we need to have polynomial. We cannot just talk about polynomial straight up. We have to say that we have to look at the polynomial that the term represents. So for term S in the language of rings, norm of S is its represented polynomial, and for terms S and T, we say that S is equivalent to T if or squiggly equivalent to T, we'll call it equivalent to T, if and only if the norm of S equals norm of T. So this just means that the polynomials that are represented by the terms are identical. Also defined for polynomials P1 up to P, we're also going to define a notion of an ideal. So for polynomials P1 up to Pn in Rx1 up to xn. An ideal IDR, or ideal R generated by P1 up to Pn, is just a set P1 times Q1 plus dot 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 Pn times Qn, where each Qi is just a polynomial with coefficients in R. So you can just imagine this is just some set of collection polynomials generated by some basis of polynomials. Well, I don't know if the basis is the right word, but just generated by a set of polynomials using the repeated, so it's generated by the set, by just taking each element, multiplying it by some polynomial qi, and then adding them all together. So when we talk about terms, t, p1 up to pn, we will take t in IDR, ideal of R generated by P1 up to Pn, as shorthand for the ideal of R generated by norm P1 up to norm of Pn. So it's just a notation. This is shorthand because just writing norms for terms, even though we know it represents a polynomial, it is messy. So the reason why we're talking about ideals is, as I already mentioned, is that we can reduce the word problem for rings to a question of ideal membership. And once we reduce, and then we can reduce the question of decidability for universal formulas to the question of the word problem. But then it turns out that we can solve the ideal membership problem in a decidable way, and also it's guarantees to terminate. You always get a yes or no, and because of that, the universal fragment of under the theory of rings is decidable. Or actually, not that's it's well. We're not going to talk about in certain theories of rings. I believe there is at the very end we're going to give a reference, and Harrison claims that there is a way to extend this for all rings, and it's found in this paper, but this is outside the scope of the presentation. However, what we're doing will apply to, for example, very useful rings like C, and also torsion-free rings, and all integral domains of characteristic 0. Okay, so the big theorem, one of the big theorems of our presentation that we have to write a proof for is theorem 5.15, which is one of the linchpins, or an example of a linchpin. So the theory of ring proves any x p1x equals 0 up to n pnx equals 0 implies q equals 0 if and only if q in idz p1 up to pn. And just note that when we have equations, we can always subtract things on both sides to get 0. So that's why we have the beginning part. So for the proof of this, note that we can replace ring proves any x p1x equals 0 and up to pnx equals 0 implies qx equals 0 with ring of u p1 equals 0 up to pn equals 0 proves q equals 0 by treating the vector x as Skolem constants. So we got rid of the quantification, and we moved it to the left.